Hello, welcome. In this short video, let us look at the numerical implementation of DTFT using linear algebra. This we want to do numerical implementation of DTFT using linear algebra. For a finite sequence of x of n of length n, the DTFT is defined as x of e power j omega is equal to the sum n equal to 0 to n minus 1 x of n multiplied by e power minus j omega n. So for implementation, we know that the omega, the digital frequency omega, belongs to the interval 0, 2 pi. So for implementation in a digital computer, we need to discretize this omega as omega k, where omega k can be defined as 2 times pi by m multiplied by n index k, where k is value from 0 to m. That is, for k equal to 0, omega k is also 0, and for k equal to m, omega k is actually equal to the final value 2 pi. We are basically making this interval of infinite possible values into an interval of finite possible values. That is, interval of m plus 1 values. So by using this discrete omega k rather than the continuous omega, the definition becomes x of e power j omega k, which is given by the sum n equal to 0 to n minus 1 x of n e power minus j omega k n. Now by using this definition, it should be equal to the sum n equal to 0 to n minus 1 x of n into e power minus j 2 pi by m into k into n. So that's the definition of the DTFT of a finite sequence x of n. Now in order to use linear algebra, we have to rewrite this definition in terms of vectors. That is, define a vector x bar, where this x is a capital X, that is a uppercase X, is equal to the vector x of e power j omega 0, comma x of e power j omega 1, and so on up to x of e power j omega m. This is basically the vector that represents the DTFT. And also define a vector of the sequence x bar, which is basically the time sequence, that is x of 0, x of 1, and so on up to x of n minus 1. So this is the input vector and this is the desired output vector. So the transformation is basically linear transformation, which we define as a new matrix W. Now W, the matrix that transforms the input sequence x bar to the output sequence x bar, is basically a matrix of size n by m plus 1. So the elements are W of n comma k, where W of n comma k is defined as exponential of minus j 2 pi over m power n times k. So this is the element of the matrix W, or nkth element of the matrix W. In the matrix form, W can also be written as e power minus j 2 pi over m power n bar transpose k bar, where n bar is the vector consisting of values 0, 1 up to n minus 1, and k bar is equal to the vector consisting of values from 0 to m. Therefore, the DTFT in matrix form can be written as x bar is equal to the product of the vector x bar, that is the time sequence x bar, multiplied by e power minus j 2 pi over m power n bar transpose k bar, which is same as x bar multiplied by W. Note that the capital X bar, that is the uppercase X bar, is a vector of dimension 1 by m plus 1. And X bar is a vector of dimensions 1 by n. And this is a matrix of dimensions n by n plus 1. So clearly, the product of this vector with this matrix should give us a vector of 1 by m plus 1 dimension, which is the desired result, that is the DTFT vector. Now let us look at the Python code that produces this result. So this first part basically gives us the theoretical DTFT, and the second part gives us the DTFT by using this vector matrix product. So this plot clearly shows that the blue dots clearly give the blue dots represent the amplitude spectrum from the theoretical result, and the green one the green curve or the green line represents the amplitude spectrum calculated by using the matrix and vector product. That is basically represents the evaluation of the DTFT using linear algebra. Thanks for watching.